NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Well, hello and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, on a very hot afternoon here in Pasadena for our monthly public lecture series called the Von Karman Series. I'm Preston Dykes. Well, 50 years ago, 3 human beings set out on a journey across 250,000 miles of space to the moon. 2 of them set down in a fragile landing craft on the lunar surface, and 1 of them stepped into history uttering a phrase that we all know by heart. But for that 1 human being to make that 1 small step took the focused efforts of hundreds of thousands of people over the course of a decade in industry, in universities, and in government. For their part, JPL and Caltech, which manages JPL for NASA, didn't play the leading roles in the Apollo effort, but for all who contributed to Apollo, as for all of us who play even a small role in the space program today, the true reward lay not in the glory of the moment, but in contributing to something greater, something that mattered. JPL's primary role, then and now, is to help lead the robotic exploration of the solar system. And that included developing guidance, navigation, and communication technologies that contributed to Apollo. JPL also manages NASA's Deep Space Network, used for communicating with all spacecraft that fly beyond the moon. But during Apollo, the Deep Space Network was used to receive the astronauts' TV transmissions from the moon. And it also was a vital communications backup during Apollo, especially during the tense days of Apollo 13. Caltech, long a world leader in the field of geology, contributed both to the field training of the astronauts and, as you'll hear tonight, to the study of the samples they returned. Tonight, we'll hear just part of the Apollo story, the road to Apollo and how JPL figured into it, and how scientists at Caltech and other institutions teased out some of the moon's greatest secrets. We'll have 2 speakers tonight, followed by some discussion, and then we'll take your questions. If you're watching our live webcast, you can submit questions via the YouTube chat. All right, now for our first speaker. JPL is fortunate to have an Emmy Award-winning producer on its staff. Blaine Baggett's first space production for PBS back in 1985 was Spaceflight, the first nationally broadcast television series ever made about the space race. One of his key advisors was Apollo 11 astronaut Michael Collins, who called spaceflight the real stuff. Blaine next turned to astronomy. He was the executive producer of The Astronomers, also produced for PBS. In 1999, he joined JPL and is now a JPL Fellow, working full-time on films about JPL's historic role in the exploration of space. Among his many honors, Blaine is the recipient of the highest honor NASA bestows on a civilian, the Distinguished Service Medal. And finally, if all of that wasn't enough, Blaine's birthday just happens to be July 20th, which is the very day that Apollo 11 made the first human landing on the moon. So please welcome Blaine Baggett.
Thank you and good evening. Wow, it's fantastic to see you all here. Thank you so much for coming out. I'm just delighted to see so many of you. And by the way, my birthday also serves as the day that we first landed on Mars with Viking. So something was meant to be, I think. Okay, maybe I better stop where I'm ahead. The more that I have come to understand the moons of the solar system, the more I appreciate them for their incredible diversity. I want to start with the outer solar system with these moons. Hyperion looks to me like a seashell. Pan looks to me like a UFO. And if we have any Star Wars fans out there, oh, I don't even have to make the reference, but there's the dark star. But there's more to the moons than just unusual shapes. Moons in our solar system are now the prime targets for the search for life. Saturn's moon, Enceladus, is a beautiful, icy world where geysers are constantly erupting, spraying out into space water ice. Titan, which also orbits Saturn, has rivers and lakes, but they're made of liquid ethane and methane. And NASA's just announced an exciting mission called Dragonfly that's going to explore Titan. And on the right is Jupiter's moon, Europa. Beneath its icy crust is a water world thought to contain more H2O than in all the oceans on Earth combined. And here at JPL, we're hard at work on a mission right now called Europa Clipper to be launched to this world. Now, these moons and many others, there are almost 200 moons in the solar system. Those moons and many others exist in the outer solar system. If we move inward towards the sun, we find a different story. Mars has 2 very small moons. Venus and Mercury have none. Only the Earth has a sizable moon and a beautiful moon. Why that is that we really have the terrestrial planets, we are all only have one large moon, is a great mystery. But I will leave the science of the moon and the engineering it took to get us there to 2 great pioneers who are with us tonight. It's a great honor and privilege for me to share the stage with them. Now, as for the present, we are in the news not only because of the Apollo 11 anniversary. We are in the news about the moon because NASA has declared we are going forward to the moon. It's the next step on our way to Mars. Now, to me, time will tell whether this is the latest case of us becoming moonstruck and whether being moonstruck is going to actually stick again. The biggest question, I think, is whether we will have the will which translates into the funding to go. Those in favor of going to the moon have their arguments. First of all, the technologies have come a long, long way in the last 50 years. And what we've learned about the moon in these last 50 years helps to make the case for going again. For instance, once it was thought that the moon was bone dry. That's turned out not to be the case. Missions by NASA and by the Indian Space Agency have found evidence of water in the polar regions of the moon and craters where sunlight, in the shadow of craters where sunlight doesn't reach. These areas are prime real estate for future exploration and settlement. There you see some examples of the water. Because if you wish to live off the land, as NASA says it wants to do with a permanent presence, you need water. By the way, India, it's scheduled for a new mission to the moon next week. It's a combination of an orbiter, a lander, and a rover. And what is its purpose? It's going to go prospecting for resources, including water. And then there's China. Its space program is growing by leaps and bounds. And China has made no secret of its interest in exploiting the resources of the moon. A Chinese rover, launched in just January this year, is now roving on the moon. And on the far side of the moon, where direct communication isn't possible, it's an impressive technological achievement. And by the way, I don't know if you know where the rover landed on the far side of the moon, but it's in a crater named after Theodore von Karman. I hope that name sounds familiar. It's none other than the first director of JPL, and for whom this auditorium and this lecture series is named after. And I can't help but wonder whether the selection of a crater named after von Karman is somehow intentional in terms of where the Chinese landed. But I'm not exactly sure what the message might be. The larger point I'm trying to make is that we may be at the beginning of a new space race. A space race this time that is a multinational one. A moon rush where the prize is to stake out regions suitable for establishing human presence. So, speaking of space races, let's now go back to the first one to understand how Apollo came to be. That means we have to go back to 1957 and the launch of Sputnik. And to help us, we're going to watch a video clip from one of my documentaries called Destination Moon, which I have butchered myself to cut it down in order to show it in a short clip. Hard to do, but better for me to do it than anyone else. So if we could, John, can we roll the first clip? Thanks.
In October of 1957, the Soviet Union shocked the world with the launch of the first Earth-orbiting satellite, Sputnik. America's response, a satellite called Vanguard, was also a surprising and spectacular event. Vanguard would be only one in a long string of setbacks for the United States space program. On a visit to the U.S. in 1959, Soviet Premier Nikita Khrushchev made sure to underscore the disparity between the two nations.
A successful moon rocket heralded Khrushchev's arrival in America, a scientific feat heavily capitalized on by Red propaganda. It gave solid foundation to Khrushchev's boasts of Soviet achievement.
America's hopes for competing in the race for the heavens rested with its newly formed space agency, the National Aeronautics and Space Administration. NASA was given an assortment of technical facilities scattered across the country. One of them was the Jet Propulsion Laboratory in Pasadena, California. Of all the groups NASA inherited, JPL was a part. This research center was then, like today, managed and staffed by employees of one of the world's most renowned engineering universities, the California Institute of Technology. JPLers were accustomed to a tradition of independence. From JPL's perspective, NASA was a newcomer with no portfolio. In contrast, JPL had built missiles and the first successful U.S. satellite, Explorer 1. JPL was led by William Pickering. When NASA asked Pickering his ideas for the nation's robotic space program, he responded with an ambitious plan that called for JPL flying an armada of spacecraft to the moon and nearby planets.
Sputnik has been called America's technological Pearl Harbor. It was a shock to the American psyche. And the reactions ranged from the reasonable, like placing greater emphasis on science and math in the classrooms, for which I suffered, to the extreme, the ideal of setting off a nuclear bomb on the moon to demonstrate America's technological capability. A number of well-positioned people in the United States toyed with this ideal. They included the scientist Edward Teller, known as the father of the hydrogen bomb, and JPL's director at the time, William Pickering. Now, what you see here is an Air Force report, because they explored this ideal to great depth, creating this report that went on for about 250 pages. One aspect of the report was to consider what science might be derived from measuring the lunar debris that would be scattered by a nuclear explosion. One of the credited researchers on the project was a college student by the name of C.E. Sagan. That's right, that's the late Carl Sagan, who would go on to become one of the world's best-known scientists and an outspoken critic of the nuclear arms race. Meanwhile, the Soviet Union continued to surprise and confound. For instance, when Nikita Khrushchev made the first visit of a Soviet head of state to the United States, the Soviets timed the trip to coincide with the first mission to reach the moon, Luna 2, like just kind of rubbing our nose in it. And just 2 weeks after that, they launched Luna 3. They took this image of the far side of the moon. It's not much by today's standards, but at the time, it was a technological triumph. And Eisenhower could only grin and bear it. Now, 10 weeks after John F. Kennedy took office, the Soviet Union struck again, launching the first human into space. Now, in Kennedy's inaugural address, he had suggested aloud in his speech that the Soviets and the Americans should explore space together. But the launch of Gagarin changed that thinking, at least for a time. And a frustrated Kennedy wrote this memo directing Vice President Lyndon Johnson to conduct a survey to find a way, any way, to beat the Soviet Union in the space race. What would it take, Kennedy wanted to know? Putting up a space lab, a trip around the moon, landing a rocket on the moon, landing a man on the moon, or any other idea? And note Kennedy's impatience. He wanted to know, are the people involved in the space program working 24 hours a day? And if not, John, why not? To get the answers to Kennedy's questions, Johnson turned to NASA Administrator James Webb and Secretary of Defense John McNamara. Webb believed the only real hope to have the first in space was landing an astronaut on the moon. McNamara didn't think even that would be enough and argued for a mission to Mars, a human mission to Mars. Well, Webb's more practical proposal won out, and Kennedy took it to Congress and now made his very famous speech proposing to land a man on the moon and returning him safely to Earth before this decade is out. What's not well known is the phrase the story of the phrase before this decade is out. It was a last-minute compromise. James Webb was given an advance copy at the last minute of what Kennedy was going to say, and to his shock, the address mentioned that there was a deadline of 1967. Webb convinced the White House to take out the year and say instead, the decade is out. Had 1967 stayed in, we would not be saying today that NASA met Kennedy's goal. But now let's turn to JPL's role in getting footprints on the moon. Even before Kennedy's speech, JPL was working on 2 moon projects. The first was called Ranger. It was designed to be a series of spacecraft that would take close-up images of the moon before crash landing. But even crash landing on the moon turned out to be a lot harder than expected. I will be asking John Cassani to relive his pain for us live about those days. But for right now, let me summarize what happened. Ranger 1 didn't work. Ranger 2 didn't work. Ranger 3 didn't work. Ranger 4 didn't work. Ranger 5 didn't work. And at this point, the lab stood down and regrouped. A year later, they launched Ranger 6. It worked perfectly, except in the last few minutes when its camera refused to turn on. No pictures meant another failure. January 30th, 1964 was JPL's darkest day. And in exactly this room, crowded almost as probably as many people as you see right now in this room, were people listening to what was going on live. And imagine what they felt like. Well, let's see if they had better luck with Ranger 7. And as you watch, be aware that you're sitting in the same room as some of the footage you're about to see of some of the people, okay? You can roll the next one.
You have 6 Rangers which fail. With each failure, the pressure on JPL became more intense, and after number 6, this was really a catastrophe.
I had no fear that the lab was going to fall apart. It was quite the opposite. Everybody pulled together, basically, what can I do to help?
6 months after the debacle of Ranger 6, JPL was ready to try once more. It had required working 3 shifts a day, 7 days a week.
The next one, 7, was a severe strain on everybody because it had to work. And if it hadn't worked, there's no telling what JPL would have been like or what would have happened to JPL. It was a sobering experience.
Launch through the 66-hour cruise was a textbook flight. 3 days after liftoff, JPL's auditorium was once again filled beyond capacity with people and tension.
Magnetic tape recorders were started at 130700 Zulu at both Pioneer and Echo sites. We are anticipating turn on momentarily. We are 5 seconds from full power. We have full power on F channel. Roger. Full power on F channel. All kinescope recorders are recording. All magnetic tape recorders are recording. Video is very strong. 10 seconds to impact. Video still good. Excellent signal strength. 3, 2, 1. Impact has occurred at 132550. All video data was excellent right up to impact. All cameras were functioning. Transmitters were functioning properly. This is Goldstone TV control. Oh, roger.
When impact occurred, the auditorium erupted in a great cheer. People shook hands and hugged one another. Some wept. One hard-nosed engineer likened the event to a spiritual experience.
Some people had smuggled in some champagne, and champagne bottles were opened. It was a great celebration.
Finally, the now humbled JPL workforce has succeeded at the moon. The television camera recorded some 4,000 images that aren't much to behold today, but at the time, they were, as a scientist in this room declared at the time, 1,000 times better than any image of the moon from Earth. Now, the Rangers, by the way, here's some headlines just to give you some sense of, I think it reveals the sense of anxiety that was relief, the relief of we had finally succeeded. I'm interested in the 2 hurt in the minor riot at the Glendale Bar. I don't know the story about that. I'll have to look that up. At any rate, so after Ranger came Surveyor. And Surveyor was a far, far more complicated mission. This was about soft landing on the moon and staying alive on the moon for some time. And let's just watch the video. I think that will tell more than I can. So John, if we can roll that, please.
Of all the questions NASA wanted answered, the most important was knowing what the surface would be like for Apollo astronauts. Was it solid? Or would layers of dust act like lunar quicksand and swallow them whole? NASA had hoped the answers would come from Surveyor. This was JPL's first experience in overseeing on behalf of NASA the work of an aerospace company. But the contractor, Hughes Aerospace, was struggling, for good reasons. Surveyor was far more technically challenging than the Rangers. This spacecraft not only had to soft land on the moon, it had to do so autonomously. It was also expected to send back images and science data from the lunar surface, not for a day, but for weeks.
That was a difficult, trying period because we were growing up at the same time that Hughes was growing up. And we didn't always mesh. A trying time.
Yes, this looks good. The aerodynamic shroud is off and Grand Bahama is tracking. As shown by the animated diagrams in the monitor, the Atlas Centaur separation has occurred.
63 hours after launch, Surveyor 1 was only 1,000 miles away from the moon, with the speed increasing as the moon's gravitational attraction beckoned.
ignition. Retro is now firing. Ignition looks stable. Falling steadily.
The vehicle was supposed to enter a fixed rate of descent. So that happens.
10,000, all signals normal. Surveyor reported in excellent condition, all signals good. 100 feet, 13 feet per second speed.
At a certain distance above the surface, the engines are all supposed to shut off. And then it's supposed to drop to the surface. And the engines all shut off. And you could hear a pin drop. It worked. We're down. It's still transmitting.
For the first time, an American spacecraft had achieved a soft landing on another celestial body. Surveyor 1 operated for 6 weeks. In all, the sturdy lander sent back more than 11,000 images before its batteries ceased to work. And NASA had the answer to its question. The lunar surface was solid and suitable for landing by the Apollo astronauts.
This is actually my favorite Surveyor image, because every single time I look at it, what I see in it is almost Neil Armstrong stepping off the lunar module. But it's not. It's the shadow of Surveyor 1 on the moon. Now, I do not want this evening to be guilty of committing the sin of omission. So I want to acknowledge that the Soviets were the first to land on the moon with Luna 9. It used airbags, which we adopted to go to Mars. So it can be argued that this wasn't actually a soft landing. And at the time, it wasn't large enough to erase doubts about whether the lunar surface would able to bear up for the weight of an Apollo lander. But it's interesting to make a comparison between the Luna 9 image of the moon and a Surveyor image of the moon. And we begin to understand that being first doesn't always mean being the best. Because what happened to the Soviet Union program, in part, was the concentration on first actually hindered their technological development. And for completeness, I have to mention one more first by the Soviets that few people know or remember. Would you believe me if I told you that the Apollo 8 astronauts were not the first Earthlings to fly to the moon and return to Earth? That's true. That's a fact. These were the first Earthlings to accomplish that on Zond 5. Now, it's easy to make a joke of this, but Zond 5 was serious business because it demonstrated the Soviets were very serious still about sending cosmonauts to the moon. But their version of the Saturn V, the N1, never worked. Now, I'd like to make one more connection between JPL and Apollo, and it has to do with Apollo 12. As you probably, if you've been watching any of the great documentaries that are airing this week and on the news, you probably know now, it wasn't well known when I did spaceflight in 1985, but that Apollo 11 landed with only 20 seconds of fuel left, something like that. And that was because the computer overshot where they were supposed to land, and they were headed towards a field of boulders. So Neil Armstrong had to take control and find a safe place to land. Well, the mission planners weren't going to let that happen again. They wanted a pinpoint landing for Apollo 12. And they wanted to make sure that they had a landmark to know where they landed. So they chose that on the moon, everything looks kind of the same. So they decided to land next to another Surveyor, Surveyor 3. And that's it that you see right here in front of you with Pete Conrad, and my favorite all-time astronaut. And behind, you can, on the horizon, you can see the lunar module that they landed in. And Pete used sort of a hacksaw to take off the camera of the Surveyor 3 and a piece of the scoop and brought it back. There was a sense, some scientists thought when they took it to the lab, that they found microbial life on the camera, that it had come from Earth. Somebody sneezed on it on Earth. It went to the moon, survived for 3 years, and went back. That's been pretty much discredited now. They now think someone sneezed on it after it got back. But what's important about it is this is exactly the same time scientists were beginning to understand that life is far more hardy and far more tenacious than we ever expected, and that there was more possibility for looking for life elsewhere in the solar system. So that, to me, is part of the legacy also of the moon landings, is that I believe now that we are right now working hard to go to these other moons in the solar system to look for life is really one of the great quests of all time. So I want to leave you with this image of two footprints, one robotic, one human, because to go on the great quest that we want to go on, it's going to take both of them. Thank you very much.
Outstanding, Blaine. That was excellent. Thank you so much. Well, with that historical background in hand, we'll change gears now to hear about some of the science of Apollo. As you'll hear, many of the elements in our understanding of the moon that we take for granted today were actually huge mysteries in 1969. And those mysteries required that new techniques and new scientific instruments be developed. After all, no one had ever studied a pristine sample from Earth's moon before. Well, our next speaker is one of the people who helped develop those new ways of studying the lunar samples from Apollo 11. What he and his colleagues learned helped to completely transform our understanding of the moon's history. Arden Albee grew up in Michigan and studied at Harvard, receiving a PhD in geology. He came to Caltech in 1959 and retired after 50 years as a professor of geological and planetary sciences. During that time, in addition to teaching and research, he served for 6 years as chief scientist right here at JPL. And project scientist, he served as project scientist for 2 years, for 2 NASA missions to Mars. Stick to the script. As well as serving on innumerable committees and boards for NASA and higher education. So for a look at the science of the Apollo lunar samples, please help me welcome Dr. Arden Albee.
Thank you. As you see, I've been around here for a long time. I wore this jacket because I found it in the back of the closet, and there's a possibility I wore it 50 years ago to the first. My daughters would say no way, but it's been back there for a long time. Mine's going to be a little bit more of I was there, and I'm going to tell you some funny things, some difficult things, some mysteries. In 1610, Galileo used a very early telescope to provide our first real knowledge of the moon. And in fact, until the arrival of the spacecraft, other telescopic work did not add much more to that knowledge. On this first slide, we see the large, smooth, dark areas which Galileo called maria, or seas in Italian. And the surrounding areas, lighter in color, which are pitted with craters, which he called craters. He did name them as craters. These intensely cratered areas, which appear white in contrast to the dark maria, became known as terra, or highlands. Indeed, they were higher than the dark-colored basins. Now, many controversies about the moon, as we heard a minute ago, fermented for generations. Extreme positions were taken by gentlemen with great eloquence, but few facts. Now, almost forgotten now is the intense debate on such subjects as the depth to which a spacecraft might sink into the lunar dust, the relative roles of volcanism, crater, and water in shaping the landscape, and whether radiation could be accumulated in the dust from the radiation from the solar system and cause an explosion when the astronaut put his foot down in the soil. And finally, the presence of exotic organisms or water under the surface. Now, many of these seem very passé to us now, but we have to remember that such controversies consumed countless hours, millions of dollars to settle, and thousands of printed pages during the development of the Apollo. The Lunar Ranger, the Lunar Surveyor projects at JPL, and the Lunar Orbiter project at Langley were all undertaken to resolve some of these and other questions that affected the safety of the astronauts for the mission. Now, clearly, we all know that Apollo did not sink out of sight in the dust, and it didn't explode on landing. But, in fact, the Apollo 11 spacecraft, the samples, and the crew were actually quarantined for 21 days until testing showed that exotic organisms were not present. Now, engineers and planners worked for a decade, more than a decade, to solve the problems of getting to the moon and back. At the same time, scientists were working on problems that would allow them to interpret the lunar samples. They didn't know at the time that that's what they were doing. In the late 40s, scientists who'd been involved in the war effort took their new knowledge of isotopes and mass spectrometry and took them back to the universities. A new generation of graduate students began to use these tools to attack problems in geology and other fields. These included some of the ones that you probably know about: the 4.6 billion-year-old age of iron meteorites, highlighting the health problems due to the lead additives in gasoline, and detailed study of impact craters here on Earth. Isotopic geochemistry was born at the University of Chicago under the leadership of Nobel Prize winner Harold Urey and others. Their students moved to Caltech and other universities around the country in the early 50s and continued these kinds of studies, and were to become critical to understanding the returned lunar samples. Well, in the mid-60s, the Apollo program began to fund scientists to develop clean labs, new instruments, and new protocols and procedures to prepare for the return of the samples. Hundreds of teams from many countries were chosen to work on the Apollo 11 samples, necessitating the development of new precision instruments and labs for the analysis of small samples. A number of these teams were at Caltech and JPL, chosen to work with different approaches. Now, I was part of a team at Caltech dubbed the Lunatic Asylum, which included quite a variety of different approaches. Now, during the quarantine period, scientists and technicians in the Lunar Receiving Lab were making preliminary studies and preparing samples which had been selected for distribution to the various teams. These samples were sent out under strict security. We had to keep them in a safe, et cetera, and an embargo on releasing any results until the Apollo 11 Lunar Conference in January of 1970 in Houston. Each team was required to arrive at the conference, turn in a written paper, give that paper, and then publish that paper without any changes. So this then amounted to a real blind test. And in addition, there was a fixed word limit. And I can remember spending my Christmas vacation in part editing and re-editing our manuscript to see if we could just take out a few words here and get a few more words in there, because that was one of the difficulties. Now, the combination of these rules set up a giant blind test of all these new techniques. And everybody headed to Houston, tense with excitement, see what others had learned, and to see if they gotten it right. But the new instrumentation came through with flying colors. A decade before, we could not have gotten all the data that we got. And if we had it, we couldn't have interpreted it because we wouldn't know what to do with it. Well, what were some of these measurements? Well, studies of the mineralogy, mineral chemistry, texture, and bulk composition of rocks are used to determine physical and chemical history. Trace element chemistry is used to determine signatures of very specific geochemical processes. Precise isotopic analyses are used to study a wide variety of chronological and geochemical problems. These samples were also examined for a whole variety of physical properties, such as magnetism and seismic wave velocity. It's probably obvious that no one team could operate with all of these techniques and methods. Well, let's take a look at this next slide. We're looking here at the lunar surface, which you've seen. Note craters everywhere, fine dust, and here and there rocks sticking up out of it. Now, our team members, like most of you now, and for in the last few days, the entire world actually, have looked over Armstrong's shoulder as he zoomed over a battered war zone of craters of all sizes and over a pile of rocks to land on the lunar surface. So here we see that surface, an array of small craters. Standing on the ladder, responding to earlier concerns about responding to earlier concerns about the mission and landing, Armstrong actually commented in the live broadcast that the spacecraft pads had not sunk into the soil. Well, our next slide that shows then that the soil looks like close up. The fine soil and the larger fragments and the larger rock fragments that you see there were all fragments broken in the intense cratering that had hurled them to this site. There was nothing that we collected that came from bedrock. Geologists are always taught they have to collect from bedrock, but there was no bedrock to collect from. With great anticipation, we examined our soil sample under the microscope and began to start our tour of the moon. This next slide shows a handful of Apollo 11 soil. It contains a wide variety of material. It is originally very dusty. You have to blow it off to see these beautiful particles. Now, in part, these are transported from a very great distance by multiple cratering events. So this soil provides an answer to the very first question we're always asked: what is the moon made of? One group from Harvard studied nearly 2,000 of these little fragments to see exactly what they were under the microscope. About a third of the fragments were of dark rock derived from the mare. A careful look identified them as basalt, which is the most common volcanic rock on Earth. And it did not take any special equipment, just an experienced eye and a hand lens to be able to make that determination. About half of them were breccias, a mass of broken rock fragments cemented by glass which had formed as a melt during the impact. About 5%, the white ones here, might help if I find the right hand. These white ones are a calcium aluminum silicate known as anorthite. Now, the team looked at these and took a giant leap. They inferred that these had been transported from the highlands. The highlands were far away. It would take multiple impacts to bring that material. Nevertheless, the material was abundant. They took an even greater giant leap and inferred that an early anorthosite, that calcium aluminum silicate, rich crust, was produced by floating of these crystals as they crystallized from the melt. So they floated to the top, up toward the surface. This idea of an early ocean of molten rock, which became dubbed the magma ocean, was embargoed until the conference and was greeted with considerable surprise, maybe even considerable doubt. Now, we expected to see irregular glass globs
But the presence of all these beautiful spheres was a great surprise, though it should probably not have. If a melt flies through not the atmosphere, you got to be careful here. If it flies through space even, it is going to tend to become spherical. The next slide shows some of these, because they were sort of intriguing. We spent lots of time playing with the balls. There were round balls and long balls and green balls. There were actually some red balls, hollow balls. See the next slide here. Here is a half a ball, which has been broken. And on this fresh surface, we see these light dots, white dots, in particular, all through this area here. Each of those is an impact crater from a micrometeorite. One of these is shown in the next slide. Here we see where the impact of the micrometeorite was. It has a molten shell around it, and then there are radial outflow of what is now glass, which was the melt, and beads going out further and further in all directions. And if you look on deeper in it, there are fractures underneath it. These cups like this sometimes broke loose, and we found those cups just floating in the soil as well. Now, one of my favorite photos is a cup like this that actually hit another meteorite. So it was a micrometeorite hitting an iron meteorite and forming one of those beautiful caps. Now the next slide shows the bombardment of the atmosphere of the Moon. Now, unlike Earth, which is partly protected by its magnetic field and by its atmosphere, the layers of the regolith sampled in the rocks and in cores from each mission preserve a record of meteorites, of cosmic rays, and of solar wind and flares. The energy of the solar flares differs between the wind and the flares, and so these particles come in and are deposited at different depths. The flares would tend to be deposited deeper in the rock, and the wind higher up. The cosmic rays have an interaction with the material in the rock and produce new elements which can be analyzed for. So these things can be used to look at what has been, for many, using all of the spacecraft and looking at different depths in soils and different depths in rocks, you can understand what the radiation effects have been for many, many time. One of the interesting things is that Apollo data showed that the average solar flare activity has not changed appreciably over the past few million years. And there were many theories up until then that solar flares were responsible for climate change. But there has not been that kind of a change. Now, high on our list of questions, because this is what the main reason our particular group was chosen, was to investigate the dark Mare rocks. Our group at Caltech received portions of them to study and to date. Upon your first sight in the lab, it was very clear that they looked a little different than terrestrial basalts. The typical volcanics throughout much of the world. And therefore, I quickly answered a question that had been asked for a million years: what's the Moon made of? We knew we couldn't tell anybody, not until we got to Houston. The next slide shows photos of a thin slice of a rock, one of the basaltic rocks, or one of the Mare rocks. And this is looking at it under a microscope, which looks at it in plain light, cross-polarized light, and reflected light. This device then allows us to identify the different minerals in the rocks, to study the texture for comparison with basalts on Earth, and in particular to see that where the last bits of the melt crystallized and what the composition was. Now, it turns out that the features which you see there are a little different
it could perfectly well have been collected from a frozen flow in Hawaii. However, when we look at the very late stage crystallization, we see distinctive differences. Terrestrial basalts always end up with some water-bearing minerals in the last interstices, typically little clay minerals. These are not present in the lunar rocks. There is no trace of water. They are perfectly clean and not altered. The other thing is that that little white thing right there in reflected light is a globule of iron metal, indicating a reducing state of that final melt that we simply would not see in a lunar basalt. So the question sometimes I'm asked is, can you tell a lunar basalt from a terrestrial basalt? Well, at first glance, they look alike, but indeed, from details, you can understand the differences. Now, this next slide is a little bit complicated. It's what we call a strontium evolution diagram. We received 5 samples of the Mare rocks, portions of them, and we dated them, each with ages close to 3.65 billion years. Now, the radioactive decay of rubidium-87 isotope to strontium-87 isotope with a known half-life is the basis for the dating. This diagram shows a plot of rubidium-8786 against rubidium-8786 because that's a convenient way to determine them in the mass spectrometer. These ratios are measured in a number of different samples taken from the lunar rock, now for ABC, which have differing compositions along this line. And if they make a linear line, like we see here, we can see that they had originally formed along this line and had decayed for the same amount of time back to that line. This is called an internal isochron, and it's what is used to measure the rubidium-strontium ages. And it is they are probably the bulk of the ages from the lunar samples are rubidium-strontium measurements. Well, again, because of the embargo, we couldn't talk about this exciting date until the conference. And we learned that other groups had gotten similar results with this and other isotopic techniques. And these results provided an absolute age for the widespread rocks in the Sea of Tranquility. And later missions dated Mare rocks from different basins. The next slide is a cartoon, if you will, which summarizes the time history of the events that have shaped the lunar history. Now, if we look down at the lower part, we're looking at the oldest part of it, and what we see there is that it is heavily cratered. No crater can fall without partially obliterated in previous craters. It's saturated with craters during this first 500 million years. Now, within it, you can see a group of basins. These basins, the lunar orbiter data in particular, that photography enabled the photogeologists to map these basins and from these basins to see what the outflow of ejecta looked like. In the same manner, the various Mare basalts are shown here, Apollo 12, 15, Lunar 24, 16, and each of those had been mapped by photogeologic techniques. And basically, you can look at the overlap relations. If it's younger, it laps on older rocks. And there you can project this through to get a relative time sequence. So on this sequence that we see on the right-hand side, shows a whole set of features which have been identified in photogeology. They provided a relative timing, a relative sequence of what had happened on the surface of the moon. But on the right-hand side, you'll see that we then have dated these various lavas. And these then allow us to make an absolute scale for this timing. So this time scale is still used today. It's applied to Earth, Mars, and other objects in the solar system, for which we can come up with a relative sequence of events, but we do not have samples yet in order to actually measure the age. Now, we will come back to this, but we will see that almost everything in the moon happened in the first 1.5 billion years. Since then, very, very little has happened to it. Now, the next one I want to talk about, in the next slide, is the mystery of the Europium anomaly. Now, this is sort of a detective story, if we will. The volcanic rocks are derived by partial melting within the interior of the planet. This partial melting, whether it's the Earth or the Moon, that's how these basalts form. Now, the major element composition of the Mare rocks didn't differ greatly from basalts, but people who worked using the rare earth elements, these are the whole set of rare earth elements, which act very much alike in most cases because they're very similar in their size and their charges. And the people have used these to understand the difference between basalts which were derived from the ocean crust and basalts which were derived from the continents. And so you can see there are distinct differences in the way the rare earth patterns are from those two sources. When we look at the lunar ones, they show a very different one, but with this striking anomaly of the element europium. Now, the interesting thing is that europium, which actually means that the source down there had to then get depleted. Somehow this had to be formed, and that europium had to go somewhere. Well, we realized from terrestrial examples that the formation of the anorthosite feldspar collects europium preferentially over any of the other minerals. And so it could subtract it. So this team, seeing this and noting it, they inferred that these crystals had formed. They had subtracted the europium, carried it away, and therefore they made the interpretation that there was an early crust which formed as an accumulation of calcium feldspar. Well, if you remember back to the start, almost the start of the talk, a group working in the East had looked at the particles in the soil and where they came from, and then interpreted the origin of the highlands as being accumulation of this same mineral, anorthite. So one group using geologic approaches on particles in the soil came up with the same answer as the group using isotopic chemical approaches. And of course, everything was constrained until we got to the conference, so it was very interesting to hear this coming from two very, very different directions, and almost from research groups that would hardly ever talk to each other. Now, we learned a lot more about this process of the floating of the upper crust by study of samples from later missions. It seems to be related to the presence of other unusual rock types. We're going to see a photo of a couple of unusual rock types. The first one is a photograph of a true anorthite in a breccia. Many of these samples were collected from breccias. So this is a sample of that outermost crust, rich in anorthite and high in europium, incidentally. The next slide shows one of an alumnus from Caltech on Apollo 17 collecting a dunite sample, a sample consisting almost entirely of olivine. And there it is, right there, where the X is. And he knocked that off and brought it back, and it shows in the next picture. The next slide. And in this case, it has been highly fractured and crushed up, and you can see both the thin section and the actual rock. Now, dunites are not uncommon on Earth. We find similar fragments of dunite and basalts that come up in Hawaii and in our own desert. Then another one is there are rocks. We'll look at the next slide. This one is a complete puzzle. I wrote 4 papers on it, and I still don't know what it's about. I ought to write another one, but I don't know any better. At any rate, this is a rock very rich in potassium, rare earth elements, and phosphorus. It's just exceedingly unusual. In a sense, it's like our granites on Earth, but we don't know how it fits in. Now, each of the samples which I pictured, we have dated. Each of them has dates of around 4.4 billion years. So they're telling us something about the very, very early evolution of the moon, but we don't know exactly what. Now, I've just used a few intriguing detective stories, and every one of the hundreds of scientists involved have their own favorites. So let me close with a summary of what I think we learned from the Apollo missions from a scientific sense. Lunar rock studies have provided the cornerstone for the scientific findings from lunar exploration by spacecraft, and such studies are still ongoing with even newer methods and samples that have not yet been studied. You may have recently heard they are about to release some of the ones that had been held in reserve and will be then available for study. And of course, we've kept splits of everything we worked on, and those are still available. Now, these findings have completely changed our understanding of the moon and its evolution, as well as that of Earth and the other inner planets. We now understand that the lunar surface features are predominantly the result of impact by numerous huge projectiles during the first 500 million years of lunar history, and that most of the younger and smaller craters were also formed by impacts, not by volcanism as commonly thought. The role of volcanism is restricted predominantly to the filling between 3 and 4 billion years ago of the mare basins, which in themselves resulted from much earlier impacts. The moon did not form by slow aggregation of cold particles that slowly heated up, as was one of the prime theories. Instead, it was covered in its early life by molten rock, from which a calcium aluminum silica rich crust formed by floating in the melt as it crystallized of the mineral plagioclase. As the outer part of the moon became rigid, the source of volcanic lava migrated downward in depth to below 500 kilometers, according to some experiments. Since 3 billion years ago, volcanic activity has been very infrequent and localized. One of the most important things, which we still struggle with, many geochemical similarities show that moon and Earth must have formed in the same general region of the solar system, with a relationship not yet understood. They are fundamentally different than your other moons. So all of this knowledge is a gift of Apollo. Thank you. Thank Apollo.
To cap off the evening, we're going to transition to a little discussion on the Apollo era as it appeared to us here in Pasadena and the legacy of Apollo. I'd like to welcome back Blaine and, of course, Dr. Albee. And they're joined by one of JPL's greats who's coming up on the stage now. In his career, he served in engineering development roles on several early launches to Earth orbit and the moon, including leading the design team for the Ranger spacecraft, which Blaine spoke of earlier. He held senior project positions in many of the Mariner missions to Mars and Venus, and was project manager for 3 minor space missions that JPL was involved in. I think they were called Galileo, Cassini, and Voyager. He also served as JPL's chief engineer from 1994 to 99. Joining Blaine and Arden is John
Well, I just have to say again what an honor it is to be with both of you. It's a privilege. What I'm going to do is ask a few questions to get us going, and then I'm sure you have questions, and so many of you are standing, and we're so appreciative of you being here. I want to make sure you get a chance to ask some questions too before we call it a night. But John, we haven't heard from you, so we're going to give you a few minutes here. And since you were in charge of the design of the Ranger, so what were you doing wrong?
What were we doing wrong?
What was your main problem that you were having in the early days? Can you talk about
They
that?
didn't follow your instructions.
Oh, right. I had a hard time getting these very liberal Caltech, JPL type people to pay any attention. I solved that by taking them out for a beer. And no, it wasn't that we had never done anything like this before. Nobody had ever done anything like this before. And JPL at that time had been involved in designing guided missiles for the Army and JATO and stuff like that. And they were a bunch of very good people there, but they were getting a little old like me and Art and are now. And they didn't want any part of designing something that new, but they knew what the principles were. They knew the things that had to be done or the way that you had to go about doing something very complicated to make it successful. Interfaces and making deals and having a way of tracking whether your progress against them. Everybody had a product and somebody's product was somebody else's input. And managing that whole concept of deliverables, receivables, schedule, documenting what you needed to do, that's what they taught us. And other than that, the rest of it, figuring out the nuts and bolts was pretty much up to us. Nobody could help us. And they were smart enough to let us go. And for the most part, we were smart enough to pay attention to what they told us was important. And we tried to do that. And somehow or another, it seemed to work.
I remember you telling me once that we didn't know what we were trying to do, and there was no one who could tell us what we were trying to do.
That's exactly right. That's right. There was nobody that we could go and ask, well, what about this or what about that? Because that was stuff that nobody had ever done before. Yeah.
And also the Rangers, just to be clear about this, the Rangers had problems with the first 6. Some of those failed just because the rockets weren't working. It wasn't just the problem of the spacecraft.
Well, yeah, the mission consists of 2 parts, right? A launch vehicle to get whatever you're launching up and going, and then the thing that you're building, the spacecraft, goes on top of the launch vehicle. So the launch vehicle guys were having problems, and the spacecraft people were having problems. Ranger 1 and 2, the first 2 spacecraft worked perfectly. But they didn't. But the missions were counted as a failure because the launch vehicle had to launch it up, put it in orbit at the Earth, around the Earth, and then halfway around the Earth, the upper stage of the launch vehicle had to ignite a second time and accelerate us out of Earth orbit. Well, the first time we did that, it didn't work, and there was an Agena upper stage, and somebody said, well, there's a relay that didn't work, and it's a random failure, it never happened again, and so, okay, bullshit. And so we did this Ranger 2, and exactly the same thing happened again. Exactly the same thing. So those counted as 2 Ranger failures, but the spacecraft hadn't failed, it was the launch vehicle. But then the Ranger 3 and 4, those were both spacecraft failures, and one of them was another rocket failure. So it was going back and forth. But from anybody, we have who's our community? Our community is the scientists and the engineers that are working on this, but also there's the political community and the politicians who are funding this, and the Congress and the newspaper. They don't give a rat's patooey, whether it was the spacecraft that failed or the launch vehicle. The damn mission didn't work, and so we had a lot of failures, one after another.
What did that do to your morale of the staff? What did it do to your morale? What was it like here?
Well, it was sort of disappointing, but I think Pickering made a good answered that question in one of your
You actually did that interview. I let you do that interview, so you like what he answered because you did the interview.
What he said was, I don't know if you picked it up in the clip, but somebody said, well, wasn't it demoralizing after all these failures? And he said, no, it wasn't. He said, because what it did, it made us more unified and more committed to find the problem, and everybody pitched in. And that's where we learned, know, it was really personal. You can't just do your own job in this. You also have to be looking over your shoulder and watching what the people next to you are doing, because what they're doing, if they don't do it right, the mission's not going to work, and then you're all goats, right? So everybody wanted everybody to work well, and so we tried to help out in whatever we could. And so I think that was good. You know, it's a funny thing about engineers. They like to solve problems. That's what engineers do. And the harder the problem, the better they like it. And one of the problems we have is you give an engineer a problem to work on it, and if he doesn't find it hard enough, he'll find a way to complexify it, to make it something more fun to work on. So that was the other problem. You know, it boils down to polishing the cannonball, and you know, we developed a saying: the better is the enemy of the good. You know, it doesn't have to be better, it just has to be good. It has to be good enough, and so in knowing when to stop improving things is just important as to knowing, you know, when to begin.
You can always fire a few managers to keep the politicians happy.
Yeah, well, well, it's that's the other thing too. You know, we don't fire a lot of people for making mistakes, and in fact, you know, sometimes a person who's made a mistake, having made that mistake, makes him more valuable or her more valuable in the next assignment because they've learned something. You've made an investment in that person, $1 million investment.
Or more.
So it didn't work? Well, okay.
All right, John, I've been waiting all night to ask you this question. All right, now we know that the Russians early on sent up dogs into space. And I have read that you were among some here at JPL thinking about sending dogs to the moon. Tell us that story.
Well, we were part of the initial task force of trying to figure out how to put astronauts on the moon. So all the centers were. We had a bunch of people. They worked under a guy by the name of Charlie Cole. They called them Cole's Commanders, and they went back to Washington, and they were helping do the architecture of this whole Apollo program. And the whole thing was going to be putting men on the moon. And there were some of us back in here who said, that is crazy. Why are you going to put people on the moon? There's no air up there. They're not going to breathe through. You can put them in a spacesuit. Then you got to get them back. Somebody said, well, why don't we train some dogs? You can train dogs to do remarkable things, you know. We can teach them what they need to do in the way of a geologist, how to use a hammer or something like that. Put them in a little spacesuit, send them up to the moon, and then, you know, when they're done, okay, they die, but you don't have to worry about bringing them back. So we actually...
You're a dog hater.
No, I'm not a dog hater. I'm neutral about dogs. But dogs have some way of an affinity for me, and so do goats. Goats and dogs love me. I'll tell you the story about the goat sometime.
Another time. Another time. So that ideal obviously went nowhere very fast, I'm sure.
Okay.
Yeah. So Arden, I want to ask about the origins of the moon. Can you speak about what some of the thoughts are that scientists have about how our moon came to be?
Well, we know because of the geochemical similarities that Earth and Moon are closely related. They were formed from the same, if you will, batch of meteorites. What we don't know is exactly how they're related, whether they collided, changed matter, these sorts of things. There are a number of, the basic theory that is now operating, and which people are working in great details of the details of the collision process and everything, is there was a collision between two major asteroids, one of which basically became Earth, and this collision combined many of the materials in the two. So that we know, but exactly the details of it we don't. Every issue there's a new, slightly different touch.
But this was sort of the theory goes, it was 4.5 billion years ago, about the time that
4.6 billion years
the Earth
ago.
was formed. About the time of the Earth was formed too, right?
Yeah, they both were formed at the same time, and the key thing really that makes them come together are the oxygen isotopes. They are so similar to each other and so different from other meteorites and so on. So it's a unique circumstance.
Sort of the same genetic or geologic code,
Right.
in a way. And how, can you talk a little bit, when you mentioned the molten sea, the ocean, did it cover the entire orb? I sort of have this incredible vision of a whole...
The highlands are that frozen magma, and they cover everywhere all around the moon. So yes, it was a cooling. It's how the moon cooled and crystallized. So.
Okay. So I'd like to throw it open to some questions from the audience. If anyone would like to come up to the mic. We have a mic over here.
I'd like to ask if there were any differences between the different Ranger probes from 1 to 6.
We developed the Rangers sort of like I compare it to Volkswagen. If you ever owned a Bug, you know, they all look the same on the outside, but if you buy one year and then you buy another one 3 years from now, it looks the same, but they've made improvements under the hood, you know, and a series of gradual improvements. And that's the way we developed the Ranger. Ranger 1 and 2 are, well, the Ranger spacecraft had to be 3-axis stabilized. You know, you have roll, pitch, and yaw. And when we did first Ranger 1, we only controlled it in pitch and yaw. We didn't worry about roll. Okay, out the side we had an antenna that had a point to the Earth. Well, the roll position mattered, you know, because that's another way of positioning the antenna, getting the pitch and yaw right, but also the roll. But for Ranger 1 and 2, we didn't control roll. And then we didn't have any propulsion on it. And then Ranger 3, 4, and 5, we put roll control so we could point the antenna. And then we added propulsion. So each one of those Rangers had an incremental capability that was engineered into it, but every one of them built on the earlier one. So it was a progressive, stepwise development.
That reminds me of the fact that the first project manager told me the story that what was thrown at the project very early on, they had not fully anticipated, was contamination. That NASA put the requirement that we sterilize the spacecraft, and that meant baking them. And you're baking your electronics at a point where you didn't realize you were going to have to bake your electronics.
Well, we didn't. That was not part of the original design requirement. Right. And I was running the Ranger 1-2 program, and we had a big battery in the middle of it. And they said, you know, you got to sterilize this battery. I said, well, wait a second. They weren't designed to be sterilized. Well, you got to do it. So we talked to some people and say, yeah, if you heat it up to, you know, 125 degrees centigrade for 34 hours, that ought to kill anything that's in there. Turned out it killed the battery, but we didn't know it at the time. And then a few weeks later, over a weekend, up with the spacecraft with a battery in it, up in our building 18, we were testing it at the time, the battery exploded, and it blew electrolyte all over the spacecraft and everything else. So we said, holy mackerel, you know, that's not a good idea. So we didn't know for sure, but we were pretty sure that it was the heat sterilization, you know, because, you know, people didn't usually do that to batteries. So, after that, we put a temperature on it and put a new battery in and cleaned it up, and we watched the temperature continually. And so I got a call one night, and I don't think it was Thanksgiving, but it was Thanksgiving weekend, and it says the temperature's going up, John. What are you going to do about it? So I said, well, and I said, call up a technician and have him meet me in there. I was in a little test chamber outside Building 18, and we climbed up on the chamber, up in a little derrick kind of a thing. And I remember this technician, I said, bring your drill motor and a 1/4-inch drill. And so when we got up in there, he said, what do you want me to do? I said, I want you to drill a hole in the top of that battery. And he said, what are you going to do? I said, I'm going to stand back here. But it worked fine.
Yes, sir.
Earlier this evening, we saw a picture of the footprint of Surveyor on the moon. We wouldn't be seeing the footprint if the foot pad wasn't in it. So did Surveyor bounce? Is that why we're seeing the footprint?
My understanding on Surveyor 3, because I've listened to the audio of the transcript of Pete and Al, what they were saying through that period, is that it landed on a bit of an incline. And so it slid just a little bit to give you that.
Okay, thank you.
Yeah.
I guess this question's for Dr. Albee. I was wondering if you could tell us a little bit about the history and mineralogy of the lunar sample that's in the museum.
I don't even know which one is in there. I don't know whether it's a breccia or a Mare basalt. These were distributed to the various centers, and I don't believe I've ever looked at the one that's in here. What number is on it? I might know it by that.
I could check if you want.
Or I'll look at it afterwards.
Thank you.
Person with the name Let's Get Outside Now wants to ask Dr. Albee, what did you think when you first held a piece of the moon? When you first had access to a lunar sample yourself, what was that like?
Well, I try to convey that. You know, when you look at that soil sample, you just have to go gas, because those glass balls just are crazy. And, you know, you didn't expect them to be there. Why you have these beautiful spheres, but you do, and they're everywhere in the soil.
And one more question from social media. Joshua Z wants to know, what do you guys think are the best ways to expose new generations to the legacy of Apollo, to the vast amount of information and what we learned? What do you think we should be doing to communicate that forward?
There's a certain thing called the Apollo effect. Have you guys heard about that? When the Apollo mission, it sort of inspired, first of all, we're spending so much money on the program, and there weren't enough engineers or science or technologists involved in the country really to do all the work that needed to be done. And so, and it was an exciting idea, sending men to the moon, and it attracted a lot of young people that would have otherwise wasted their college years being lawyers or doctors to go into science, engineering, and technology. And I think that was really the thing that made the whole space program eventually possible. You know, all the things that we're doing today and done afterward, you know, whatever they are, all happened because of that influx. And other countries, I think, jumped into on the wagon too. China and India and everything else. They know about the Apollo effect, and that's what they're doing. And that's why they're in it now. You know. So I think the thing to get people in is to make sure that the missions we do from now on are not just science missions, you know, which is good, but are not just technology missions, which are good, but are publicly engaging, that are missions that capture the imagination of young people and get them interested in it and following it. But you know, what the hell do I know?
All right.
What brings kids into college?
Okay. All right. Thank you. Next question.
Hi. As we enter a new era of spaceflight, what are the most important lessons to remember from your era of space exploration?
Well, there's a continual transition. You have to remember, Apollo basically had no computers. And now a spacecraft is filled with computers. I mean, the whole arrangement is different. When we flew Mars Surveyor, we basically had a network on board connecting all the instruments, the spacecraft, and all the parts of the spacecraft. It basically was like a Wi-Fi network. So that amount of transition happened between Apollo and the next few missions that JPL began doing.
And what about you, John? What advice would you have to the next generation of engineers and scientists?
I mean, there's so many dimensions to that question. If you're talking about what does it take in terms of engineering and development to make something successful, or how do you coach people to do things so that they'll last a long while? Well, we learned that very slowly and very painfully over a long period of time. And it used to be the main problem was twofold. But the first one was parts, electronic parts. You know, we didn't. Most of the things you had vacuum tubes. You know, that you couldn't depend on a vacuum tube to last more than 3 or 4 years. If you had none of you are old enough to remember television sets with vacuum tubes, but you know, you'd have to call the TV repairman, and he'd come up with his bag of vacuum tubes and put a new vacuum tube in. Or he'd say to your wife, you know, when you plug the vacuum cleaner in, you got to remember when you're through vacuuming to plug the TV back in. We had a lot of calls like that, and then things would fail. And so when we got into transistors, were invented in 1954 or 1953. I was still in college, and I was learning about vacuum tubes, and they brought these transistors in. And then they said, you know, you couldn't even get a shock from touching one, so people didn't believe they could do anything.
You asked about what you could do, invent cell phones, because if you sell 1 billion cell phones, you put an incredible amount of money into developing new techniques. I mean, all these micro spacecraft, which we're talking about, owe it directly to cell phones.
Yeah, but in the development program, something will go wrong. Something always goes wrong. And the thing of it is, when anything that goes wrong, you have to follow that to the root cause. You have to drill down and find out exactly, to the degree that you can, what happened, and then do what you can do or what you need to do to prevent that thing from happening again. And that's tedious. And it's, you know, but you have to have that discipline. And unless you have that discipline and instill into the young people, you know, the need to do that, because they just want to fix it and then go on. But just fixing it and going on doesn't mean it's not going to happen again. You have to find out why it went wrong and fix it, and fix the thing that caused it to go wrong, and then you're on a good track. But that takes discipline, and it takes a lot of tedious work, and it's not fun always. You know, that's where. Yeah, that's why you go out and have a beer at the end of the day.
Thank you. Building on that, I think the two things, looking from my perspective, what I see engineers working on is miniaturization is very, very key. And the second is the complexity of the software. These days, it's software oftentimes what's going to get you before the hardware. We've got time for just a couple more questions, I think. So, yes.
Okay. So that idea, brilliant idea of setting off a nuclear bomb on the moon is very intriguing to me. Who talked Robert McNamara down, and what was the story behind that?
Oh, no, it wasn't McNamara.
Okay.
It was, well, I mean, there was someone in the Department of Defense, in the Air Force, working on that. But, you know, our Defense Department's always working on ideas. You know, crazy ideas. They're working on crazy ideas now, but some of them end up being technologically interesting and good ideas. So this was just one of them.
They didn't know about space debris?
Did they know about space debris? Yes. Yes, I'm sure they did. But to what it would do in terms of, you know, 250,000 miles away, I don't know if they were particularly worried about that aspect of it.
Okay, thank you.
Okay.
Hi, I'd like to know which of the 7 Ranger probes cost the most based on the parts used to build them.
It's a budget, you know, a guy here. We've got an accountant on our hands.
Well, I don't know if we could actually identify the cost of each individual Ranger, because they were built as a program, you know, but each one had more capability and was able to do more things. And so, you know, the Ranger 3, 4, 5 costs more than Ranger 1 and 2, and Rangers 5, 6 cost more than 3 and 4. And then because there were so many failures, you know, then we had to bore in on those failures that I was talking about before. That meant more work, more people, more time, more testing. So each one of them, I would say, would cost more than the one before. And so the most expensive one, which would have been the last one, which was, what, Ranger 10, I guess. Yeah.
That's about all the time we have for tonight. I'd like to thank everyone here and online for joining us, and thank you to our speakers. So join us again next month for our show on comets, asteroids, and dwarf planets. It's the big science of the small worlds. We'll see you then. Good night.